Now we're going to have a look at the linear phase EQ, and that's a set of two plugins. Firstly, this one here, which is the main one really, which looks like a traditional EQ in terms of it's got 5 bands, well actually 6 here, but 5 main bands that are all identical, and over here sort of a dedicated single low end band. And then this second plugin over here, which is known as the linear EQ low band version, and it's got 3 bands all dedicated to the low frequencies. Now we'll start with this one first and go from there. But first, a question that many of you are probably asking: what is a linear phase EQ as opposed to an ordinary EQ? Well, an ordinary EQ is what's known as a minimum phase EQ. And what that means is it does invariably impart some form of phase shifting to the sound. Now, when we say phase shifting, we're not talking about that sort of deep sucking effect that we used to get on 70s psychedelic music or that you put on your Fender Rhodes piano. But I mean, in many ways we are talking about that effect, but nowhere near at that level. This is a much more subtle thing. Every time we change a parameter in a minimum phase EQ, we are actually creating some phase shift. This is not the case with a linear phase EQ. Linear phase EQs have what's called a fixed group delay. That is to say, if I do something over here like do a big bass boost and push this up, all other frequencies will be delayed to catch up to this bass. Now, of course, low frequencies travel slower than high frequencies. So now this bass here, which would normally slow down and create a phase shift, the entire output of the plugin will be delayed so the bass can catch up, so to speak, and then the whole thing will be output in synchronous. Now, this is a pretty complicated subject, especially if you're not mathematically minded or scientifically minded, and I'm one of those guys. I mean, the mathematics of all this goes completely over my head. But if we just have a quick look at Wikipedia, and this is, again, getting a bit geeky, but let's just go to the absolute minimum that we need to understand here. And over here it says, linear phase is a property of a filter where the phase response of the filter is a linear function of frequency. And that just simply means that the whole thing will output at the same time no matter what we do to it. If we boost or cut, whatever, the phase of the EQ will remain intact no matter what we do. And just this last sentence here, since a linear phase or generalized linear phase filter has a constant group delay, all frequency components have equal delay times. That is, there is no distortion due of select frequencies. Now, really, that's all we need to understand. There's no distortion caused by boosting or cutting as opposed to a normal EQ. Now, the first time this was explained to me and I understood this, well then you would think, fantastic, I'm never going to use a normal EQ again. I'm going to be linear phase all the way. But then there's another side to that coin as well. Linear phase EQ does have a certain sound to it, a kind of cleanliness, almost, I guess some people might think, sterile sound, in that it's very pure. It doesn't color the sound in unnatural ways. But yet, for so many years of EQ, since the existence of EQ, we've been used to minimum phase EQs and EQs that do color the sound in a certain way, and we like that sound in most cases. So in a way, you've got to train your ears again, because this is a new phenomena. I mean, these things have only been out on the market for 5, 6, 7 years maybe, and that's because they are so processor intensive. And it's only in the more recent years that the calculations can be dealt with properly by our computers within a reasonable usable time. And because of the fact that it's so processor intensive, we have a price to pay in latency. So we'll just have a look down here now. Now, the latency here is blown out because I've got 2 of them on there, but 4,800 samples. And, just for one, for instance, I'll just make a new track. Okay, so there's another track there. I'll just option drag a copy over and have a look. And we can see 2,800 samples. So it's quite a lot. It's definitely too much to use in a tracking situation. I mean, it's really totally unusable in that context. And in many cases, it might be too much to use in a mixing situation as well. I mean, in my case, Pro Tools HD will compensate for it as long as I haven't got that strip full of other stuff that might push me over the limit. But yeah, I could use it. It would be compensated for, but it's kind of kludgy. The whole track ends up having to be delayed significantly. Ideally, linear phase EQ is not really meant for mixing situations anyway. The whole purity argument and all that seems to lend itself much more to mastering. So now let's have a listen to it. Now, it's a difficult thing to demonstrate because largely it's just going to sound like an EQ. You're not going to sit out there and think, wow, that sounds totally different to a normal EQ. So you've almost got to take it on faith and then try it out for yourself to prove that it does sound extremely kind of invisible in a way. It's the EQ I would reach for when I don't want to impart any personality onto the sound. So for instance, if I've got a track for mastering that's kind of quite anemic, it's all been done, maybe a bit on the cheap, it's a bit thin, could do with as much attitude as you can give it, then I probably wouldn't reach so much for the linear phase EQ. I'd be reaching back for the Pultecs that I showed in the earlier tutorials, because they've just got more vibe about them, they've got more attitude about them. But by the same token, if there's then a problem in that track, like maybe some ringing in a bass, or nasty cutting high mid frequency that's getting to me, I definitely reach for this fella here and dig those offending frequencies out. What is fantastic about linear phase EQ, because of their phase linear nature, you can actually dig things out, do some quite aggressive cuts without causing much spectral damage at all. So that's another benefit, as well as some nice boosts that they can do. So let's clear this guy off. Okay, now I'm going to play this track again by the band The April Tree, and what I've done in front is use this L1 purely as a gain reduction device, and I've just taken 9 dB off the ceiling here, and that's because I'll be doing some pretty hefty boosts to give examples here, so we need that headroom. Now, what's amazing about this EQ is that it's got so many filter types, and some pretty amazing ones that you don't see ordinarily in other EQs. So looking at this main plugin first, we've got 5 matching bands there, and when I say matching, that is each one will go all the way down to 258 Hertz and go all the way up to, say, almost 22K there. And that's the same for that one, and that's the same for that one, 258 down and almost 22 up. So they're identical, but look at the different filter options we've got inside each one. That's quite a choice, and some of these, as I said, are pretty weird, so let's go through them. So of course, we've got the standard parametric bell, so no secret there. I'll just bring it down more into an audible range there. So no secrets there, we know all about that. Gain, choose your frequency, and of course, pick your width. Then we've got the standard resonant filters that I talked about earlier. So that's a resonant low shelf, which is going to be strange from that position. So I'll bring it down there so it's more of acting as a low shelf. Now what's amazing here is using the Q control as the amount of resonance control. Look how crazy and steep we can get. Just looking at the graphic display, of course, we're not hearing this now, but just so you can see. So there it is, kind of a standard flat thing, but we can get very, very resonant. So, I mean, that's super peaky, and look at the overshoot in the downward direction there. It's wild. So let me play that and you'll hear, you can create, I mean, these are almost not useful sounds. They become very much like effects. So I'll just go from there's our flat sound, just so we can hear that. Okay. So, I mean, you can really hear the resonance, where they start sounding like effects filters. So of course, if we were doing this for a standard EQ job, we wouldn't be quite so resonant. We'd bring it down to a more sensible level, maybe something like that. There we go, you can get a quite nice bottom end from that. Anyway, that's the resonant low shelf. So I'll just jump one now and show its matching version on the other side. So that's the resonant high shelf, obviously. And we'll get away from 258 down there and move up to a standard sort of high shelf boost. So say around 5 or 6K, let's hear that. So very bright. But again, we've got that crazy amount of resonant boost. So again, large variation that you can put in there. Now let's look at these V slopes, or variable slope low shelf. Now, these are amazing in terms of their kind of brick wall nature. I mean, watch this. Okay, fine. This is a low one, so we'll go down low. I'll boost it up a bit. So it looks like a normal filter, but when I go for this Q control, look what happens. Other way. I get quite a steep wall here, and that'll be a huge boost now. Let's have a listen. Okay, way too boomy. But look what happens when I move this up to a higher frequency now. I'm going to do this from a control surface actually, so it's a little bit easier. Look, it's getting steeper and steeper and steeper. Now look at that. I mean, that's a filter. That's amazingly steep. So let's listen to that, which of course will be just a huge boost and then a bizarre drop. I'll go a bit higher. So So again, the range of control we get is just bizarre and can be used for great effects as well as possibly some problem solving. Now, I'll keep going down here. The variable slope high shelf will be exactly the same. We'll just have a quick look, except in the other direction. As we go down lower, the slope gets slighter because of the calculations involved, I would think.
Make things happen while I was just standing still. Couldn't this be somebody else?
Okay, next one. Then we get the resonant high pass. So, of course, I'm using that on the wrong end of the spectrum here, so I'll have to scan down. Okay, and I'll tighten it up with changing the Q. Right, so what you see now is a standard kind of high pass filter, except it's very high. I mean, 258's as low as you can get in this section of the plugin, but we'll move on from that in a minute. So it's a standard high pass filter at this point, but as you saw when we first instantiated it, as soon as I move the Q, look how resonant I can go. Again with the filter sweeping. So possibly this might be more useful at the other end where we go for a resonant low pass. So I'll move that up higher. Now that clicking you can hear is something I was going to talk about next. Because this is a linear phase EQ, it's making amazing calculations which it needs to actually buffer and then spit out, so to speak. So, I mean, just quickly I'll show you the bottom end and it's much more obvious there. Let's clear that. Now, I'm just going to play now and start adding some boost to this low band here and just listen to what happens. As soon as I let go of the mouse, click, click, click. So every time I let go, or even worse, I'll sweep some frequencies. So that's the EQ recalculating as I let go. Now this effect is actually even more dramatic in the low band version, which we'll see in the next movie. But that's just par for the course for using this type of EQ, and there's nothing we can do about it. So because of that, we don't recommend that you automate filter sweeps or whatever using the linear phase EQ because you'll be in for a world of hurt. Now the last two filters we're going to look at are the V-slope low pass and high pass. Now, once again, these are a little bit extraordinary compared to those found in ordinary EQs. Let's look at the low pass first. Now, I'll push that up to a higher level here. Now, as you can see, again, this incredible steepness there. So we can use this Q to go out to something that looks more like a conventional low pass, but then the incredible steepness takes it somewhere that we're not used to. So let's have a listen just at that level. Okay, fine. So I'll open it up a bit. Right, now watch what happens when I steep it up with this fella. So again, it's almost like a complete drop off a cliff. And again, you can hear the ringing in the filter or that sort of resonance. Now, it's not the resonance in the normal way where it's overshooting and creating a resonance, but it's just so steep that it creates that ringing effect. And just to compare that to a standard filter that would be used to, which of course would be just the ordinary kind of resonant low-pass filter, but not at such a savage amount. So we'll get rid of that resonant bell. So a normal low-pass might sound a bit like this, which is a bit easier on the ears. It just sounds like lo-fi at that point, for instance. So that's more like a lo-fi sort of experience. But then here, I mean, it's crazy. Yeah, and you get the ringing. So you get the idea. And just quickly, the V-slope high pass is the same thing, but at the other end. So away we go. Now again, because we're dealing with this group of 5 bands here, 258's our lowest. So again, very steep. You can still hear that ringing a little bit when I move it. So as you can see, there's a huge complement of filters here. If you can't solve your problem with this set of tools, then maybe EQ's not your answer. So now we're going to jump over to the low band. Now with this low band, there's less choices. So this is the standard bell, a low shelf, high pass and low pass. So that one's a bit more traditional. And Because of the complexity of the plugin, that's why we've only got this one kind of low band, which is broken off, designated by that line there, broken off from these other 5 here. And if you need dedicated bottom end surgery, that's why we go to the other plugin, the low band version. Now we'll just have a look at some of the other controls on here. Over here we've got a 12 dB or 30 dB scale switch, and that's just to do for the display. As you can see, some of these resonant things can get pretty steep, like we're off the top of the chart here. So if we flick over to 30 dB, that just scales this scale here up to a 30 dB maximum or minimum down there. So now this crazy boost doesn't look quite so crazy, but in actual fact, wow, look at that. Pretty steep. So that's that. Over here, the dither control. Now, this has nothing to do with the final dithering for your master output, which we're going to talk about when we deal with IDR in a few movies' time. This is to do with internal dithering of the plugin. Now, this plugin operates internally at a higher resolution than does your native workstation system. So in my case, Pro Tools HD feeds in and out of plugins at a 24-bit resolution, but in this case, this plugin deals with its internal data at 48-bit resolution. So the dither switch here is basically saying to us, when I output sound, shall I dither my 48-bit result back down to 24 or not? The opposite being, shall I truncate my 48-bit sound down to 24? So dither in this case is a tiny amount of noise which is applied to the softest part of the signal coming from the plugin. And I mean, I'm talking really soft here, 144 decibels down. So it's not noise that you're going to necessarily hear unless something's terribly wrong. So you would always want to dither. I don't quite understand why you wouldn't want to dither in this case, because as I said, the opposite is truncation, which means that those 24 bits of the bottom are just thrown off, and technically you could be left with some horrible digital grunge at the bottom of your noise floor. Again, it probably isn't going to matter in this case. I mean, we're talking so far below zero that it's going to be inaudible, but in terms of good practice, you would want to dither. So I suggest just leaving that to its default, which is in the on position. And now we're going to talk about this section down here called method. Now this is some pretty geeky stuff. I'm not going to spend a great amount of time on it because it's really very complicated and quite scientific in many ways. So if you want to look into this more, feel free to go through the manual and even do some other research on filter design because it gets pretty full on. So just quickly, this section method has 3 options. It defaults to this one called normal, and there's also accurate, and there's low ripple. Now as I click these, you can actually see the display here changing. I'll just go through it again, just a little bit. And this is actually a way of designing your own filter or designing the response of the filter. And every selection you make has a benefit and a trade-off. So I'll give you an example. I'll put it back to normal and we'll clear that one away so we're not looking at it. In fact, let's just switch this over to, say, a bell in this case. So a normal bell. Now, an example here is I'm going to say 4K. So 4,000. Now you'll watch, I can't actually get exactly 4,000. And the closest to 4,000 with this EQ is 3962. And this is something we haven't yet talked about. This is not a continually variable EQ that we're used to, where we can literally type in the frequency we want down to like a single cycle or something. It basically works in steps. And the higher the frequency, well, the closer the steps appear to be. So if I want to go to 18K, I can go to 18,002. And the next step up might be, I don't know, let's go to 18,009. Nope, see, it forces me back to 18,002, 18,020. No, it's still 18,002. So if I try and do it with a mouse, it gets a little bit tight, but okay, boom. So 18,002, the next step is 18,174. So the steps are, I guess, a little bit still broad there, but that doesn't seem like much of a step. But in the next movie, you'll see when we talk about the linear phase low band that the steps are actually quite broad down in the very low area. But anyway, moving on, I'll go back to 4K. And I'm going to set this for its tightest, so 650. Now let's do a cut as great as we can. So we'll go down now, -30. So that's the other thing. These EQs are like -30 or +30. The range of control is much greater. Now, as you can see, I'm -30 here, but the filter seems to have sort of stopped there. It doesn't go any lower. Now, I'm looking at a scale of 30 set with here. So this has gone to about -18 or so. You can see there if I put it in the 12 dB scale, it has gone off the bottom there. But here it seems to stop at about -18. So if I change this now from normal to accurate, let's see what happens. Bam, it's gone all the way to the bottom now. So as its name implies, it's accurately given me what I've asked for, a 30 dB drop. And if I go to low ripple, it bounces back up again, not even as far as normal. It's probably gone to about, what, -12? No, it's gone a bit beyond there. So for this specific task, accurate is the one you're going to want to use if you want to dig the deepest hole to notch something out that you can get. But let's go to a different task. Let's say a variable slope low pass. So here we go here. Now at the moment we've got like a virtual falling off the cliff as we've looked at previously. That's in low ripple mode, but I'll just jump through these and let's have a look at the difference on the board here. Now this one, we're not going to see much difference, but I can tell you now that accurate is again, in this case, is going to be the steepest one, the one with the tightest right angle here, but that comes at a price, and we can't actually see the price on a display here, but the price is that this slope going down here will run out of puff, so to speak, at a higher point. Now that point might be like -60 or something, which is possibly not even relevant to what we're working on, depending on how sensitive the material is that we're EQing. But these other approaches here may continue that downward slope further down. And that's what's known as the stop band, the point at which the slope kind of runs out of puff, so to speak. So the stop band will be lower on these other ones at the expense of being not quite as much of a right angle here. So like a lot of things, it's a compromise depending which is more important to you. But as I said, these are pretty high-tech kind of things to worry about. In an ordinary mastering job, I'm not concerned about things like this. I'm not concerned about having the filter that's the absolute steepest in this sense, versus where it stops 60 or 70 dB down below zero. But for the sake of education, we need to cover all this. Now, we'll just look at one more thing. Let's go to, say, a resonant low shelf. Okay, so now we'll go something like this. Yeah, maybe something like that. Now let's go through the methods here. That's low ripple. That's normal. And look, that's the accurate mode. And things are breaking up a little bit here. Now let's have a quick check. Now, because I'm doing something crazy, I'm going to pull this down like significantly, like, I don't know, -20 or even more. Let's see how loud we are. Still a bit loud, so I'll go even more. Doesn't really matter. So I'll pull that right back. Now let's jump through the various methods while we listen to the result. So significant change in frequency there. Low ripple. And normal and low ripple are very similar. But this accurate method is ringing like crazy, isn't it, around here? Okay, now as to the actual sort of scientific phenomena of what's happening there, it's beyond me. It's probably beyond most of us. If we want to just play the artistic role, just flick around the switches, see what works well for you. But it's good to know that there's so many options available with this EQ if we need them. So that's all we're going to talk about with the methods. We'll move on now, and in the next movie, as I've said several times, we're going to cover the partner EQ to this one, the linear phase low band. So I'll see you there.